Okay, so I will start. So really thank you for coming. Well, I'm very sensitive to this first slide. When you see this shape of blades, you saw probably around our stand H160. Okay, this helicopter is full of the innovations, starting from vehicle, gearboxes, avionics, and one of the main breakthrough technology is this blade. Okay, and it is really the way we want to generate value for the customer, to do things with the most cost-efficient way, bringing really the value. And the value here is really everything what touches the environment. The noise is the main item. Only with this shape of the blade, we were able to reduce at least 3 dB. It's divided the power of the noise by factor 2 due to the shape of the blade. And also, it's a virtuous circle, because with the shape, we not only improve the noise, but also we improve the performances and reduce the vibration. This aircraft has any anti-vibration devices. So, well, it's really the way I would introduce the second slide, where really we want to, through innovation, generate the value for the customers. And it is, I think, the really strategic priorities for the company. Customer loyalty. So we want that the company becomes customer focused, less product technology focused. So the previous example shows you the improvement must be done in a way it really brings the value in a cost-efficient way to the customer. Fast-growing markets. So there were a lot of discussion about the urban air mobility. So we will play this role not only as a vehicle provider, but supplying end-to-end solution. End-to-end solution is also integrating the maintenance and all the people, customers often wants everything, to having everything integrated. They have the less burden to operate our aircrafts. So of course we want to make the vertical lift the best choices. And well, it is what we are attached. We are much attached for saving lives. So in many countries, we see our helicopters flying in the hospitals. So it is something really we are very attached to it. We have also the helicopter which can climb, okay, to take people in the mountains, something what the company is really much attached. Protecting people. And this is, I will show the examples. We go also to new military application, like the drones. Okay, reaching everywhere. Our helicopters should operate in all the conditions. Connected cities. Okay, so we are speaking about urban air mobility, but also we consider that we can connect cities in a quick way. Okay, so there will be the business in the cities or between the cities, and for this I will show you we have different solutions. So, well, this is strategic chart we use in-house the company, how our business is distributed. We have everything what is the short-term solutions, improving actual fit with new technologies we developed. We use for this the demonstrators, when you see here, and we have in the longer term the vision for the urban air mobility. We are very active in terms we are testing prototypes, okay? Because testing in this area is really the history of the company to get very quickly to the best technical solution, safety, performance, cost, environment. Flagships to validate the technobricks. Okay, this is the logic. And well, I am always very proud when in the forum I see on the helicopter something we develop in terms of the technobricks on the flagships that is integrated on the products. And this was, I was very proud, okay, to see on the H145 2 technobricks we developed on the demonstrators before. One was the BlueCopter helicopter you see on the top. We tested several technobricks. And on the 145, quite quickly, 2 years later, you see integration of these technobricks in real life in order to give this service to the customer improvements. We have 5-bladed rotor, BMR, which is completely new technology in terms of the shapes of the blade, what is in, dynamic tuning. So we improve significantly the vibration of the aircraft. We improve the performances, some 100 kilogram more takeoff weight, and also the mass reduction would give to the aircraft 150 kilograms more useful load. Respecting vibrations and also integration in the global aircraft. Also, we tested on the BlueCopter wireless onboard communication system in the second technobricks, which is integrated on the H145. And really, what is important here to show this logic, okay, going through the real demonstration, and the real demonstration is done. We have the 36, and then quickly going to the product. And it's really the first line of the logic improvement of the actual fleet with really the new technobricks. And well, on the BlueCopter, you see also another components probably which will come very soon on our fleet in other areas, because the amazing thing is that when we have such a demonstrator, there are several technobricks. Some that are visible externally, okay, some there are in-house control systems, let's say actuators, and these technobricks progressively also will join our actual products. Okay, this is the logic now. We are in the second part of our logic, okay, where we have the demonstrators. So I will start from this side. We have VIA700. It's based on the 750 kilograms Cabri helicopter, where we have flown completely autonomously over populated area last year, the aircraft in autonomous way. Okay, we integrated all the actuating system, control system, autonomy systems in this aircraft. We have the racer. You could see it's on the mock-up. We will fly it end of the next year, putting a lot of technology. I will come later on this, flying 50% quicker than the normal helicopter with 20% less operating cost. And we have a very aggressive approach for the urban mobility, and well, I will come to the later on. And you have here the technobricks, okay, that we will test on our eVTOL flight lab. Flight control, this is still to be improved in terms of the computer, in terms of the actuation system, to introduce the improved AFCS, or cost-efficient fly-by-wire system. Electrification, I think we were discussing it recently about the electrical backup system. It's a system we can put electric motors, we can put on the gearbox on the single engine operating helicopter to improve auto-rotation capabilities. Extra power, and even in some conditions, we could even have 2 minutes electric flight in economic speed. Okay, so this is a real area of noise, but noise also is related to electrification, because when we put electric system, we can reduce the rotor RPM. As you know, rotor rotational speed, tip speed, is key factor for the noise. Whenever we are able to reduce the tip speed in an efficient way, then the noise go quickly down. It's roughly power 3 of the rotational speed on the first order. And with electric system, it's very efficient, because when we reduce the RPM, we go closer to the stall, and with very dynamic electric system, we can very quickly increase the rotational speed in a quicker way than normal turbine. So this makes a complete logic how this electrification can support entry into urban environment in an acceptable way. Yeah? Okay, so let's come to this demonstrator. So we have on the top CityAirbus. So I was just last week in Donauwörth when we first have the rotations. Okay, last week we were to 50% nominal speed, but this afternoon I have just a message. We are nominal speed, let's say, still on the ground, and well, now we will look on the data, and then we will make flights. So it's really now basic innovation principle of the company is always going very quickly to the testing. Yes, and this is really the key. We really want to test different architecture because before choosing the optimal one. The second one is the Vahana. There was a conference this morning, okay, where we have a different principle. First one is based on the drone principle. We have 4 double rotors, okay, without tilting mechanism. Another one, we have the tilting wing, okay. So there are 4, and again, the elements is the best way is to test it and to find the compromise. Vahana was doing also the flights. And well, on the CityAirbus, it's really great for me to see the team, okay, how people learn, let's say, how we introduce this electrification in the way of designing the aircraft, way to test the aircraft. So it's really, really very important for us to have in the teams really this know-how. And the racer, you have here the mock-up. So really, we want to go faster, 50% faster. 20% reduction of the cost per nautical mile. And it is done by the aircraft, which is a very good compromise between the complexity and the added value. Okay, there's normal helicopter rotor, which gives very good hover capabilities. Yaw control is given by 2 propellers, and in forward flight, we unload the main rotor using propellers, and half of the thrust vertical lift is given by the wings and half by the main rotor. And this is something what we tested in X-Cube. And the racer, which is the new generation, have several improvements. Now we have the pusher propellers. When the propellers are behind the wing, we improve efficiency. We decrease the power in forward flight, because the wings generate the movement to the air, which is counteracted by the propellers. And the dissipation of energy behind is much, much lower. So it gives at least 10% of the power need decrease. So the range is improved by 10%. Also, this double wing has another advantage, that we have less downwash, okay, because the surface of the rotor, and we have 2 surfaces, so it's important and improve significantly the performances in hover. We can also integrate the landing gear in the lower wing, what is very good for architecture. You have a very good positioning of the aircraft on ground. And we have also the hybrid start and stop system, like in a car industry. We can stop the engine at 180 knots, and we use the full power of the second engine, and the fuel consumption goes 20% below. It's known that the turbine specific consumption goes down with the power need. So it's better to make work in 1 turbine on full power. The 2 turbines on half a power is much more energetically efficient, but you must start the second turbine if necessary. It is done by high voltage, started on system like in a car, but it's a system which is much more powerful, and the turbine can recover very quickly the power. So this we will test on the racer. Okay, few words about the autonomy. So it is something what we like a lot, comparison between automobile and aeronautics. It's something, I spent 3 years in automobile, and something which is a bit in my blood, so I like it a lot. So here you have, let's say, what, it does not work. We have 5 levels of autonomy. Okay, level 1, 2, 3. All the safety is based on the pilot or on the driver. Okay, so there is no any liability based on the OEM. Okay, and level 4 and 5, liability is on OEM side. So this is how automobile industry is working. So we have the level 1. You have in your car jam traffic assistance when you have the car in front. You have the radar, okay? This radar catches the car in front, and you can follow the car playing on the brakes, okay, and changing of the reduction of the gearbox, okay? You have what doing Tesla is the more clever one. You can change the line. Is you electrically your steering wheel, okay? And then progressively, you know, with the full autonomy, level 4 is in some areas, protected area, it flies everywhere. So that's roughly how it works. And we follow roughly the same logic with, so you have, I took here the Igor Sikorsky as no automation, the first the first example. The second one is the what if automatic pilot. It's already automation. And we have the cable detection ERSAS system. It is something which is based on the leader, allows the pilot to see the detection, and the radar gauge the cables in front. Okay, so this is something what is important. It's the first step. And the second step is the sense and avoid. It's something what we have a small film I will show you. I will just explain. It's called I for augmented landing, for augmented guidance and landing extension. So it's the system based on the camera which catches, we distinguish the area of landing, and then is coupled with automatic pilot. It allows the helicopter lands automatically, and you will see the test we did just last week. And our communication people took really, in the latest moment, this film. So you have the Eagle, you have 3 cameras, gyro stabilized. It's mounted in the front of the Super Puma. You have on the screen here of the Eagle. So this camera, how it's controlled, is fixed on the left side. Okay, it's the external camera. And on the left side, you see the helipad. And then his helipad with the artificial intelligence gives you trajectory, and this trajectory allows you to land in the area you are looking for. But always, like it's level 2 of autonomy, is still the pilot who has the responsibility of it. If pilot considers everything okay, he is okay to the system, and the system automatically lands. So we roughly follow what is done in automobile. Is good in the history of automobile. Sometimes automobile is the front, sometimes aeronautics. But this mixture and the exchange is really very useful. For instance, a lot of sensors also we are using coming from automobile. And here for full manned application, we have 155. We did it already a few years ago. H145. We did autonomous landing in, it was a few years ago also. And now Vahana CityAirbus inverse VSL 700, which now flies autonomously over populated areas. This is the CityAirbus picture last week when I was in Duna World. So, while in the construction, you see 2 propellers, okay, one below another, and propeller below is shrouded. Is it shrouded? Why? It's shrouded because we want to improve the performance in hover. Okay, and this is really extraordinary that performance of such a solution is equivalent to the normal helicopter rotor, even better than this, due to the shroud. Okay, because principle to use the lift, generate the lift, you must take the air from the top, put it through the rotor, and you generate overpressure below and pressure which is lower on the top, and difference of pressure multiplied by the surface generates the lift. And here you have a bigger surface, okay, so we have more lift. So just to give you the idea, one shroud is 20 kilograms, and it generates a bit more than 100 kilograms of lift. You have 4 of them, so you can imagine. So you are a student, perhaps you will do one moment your PhD on it. I really recommend it. A helicopter is a business when you're young, you still dream, 30 years ago. I can tell you from my experience. So the second thing that the system is completely redundant. Okay, if one propeller is off, the second propeller can in half a second recover completely the double of thrust. So on this, we have 400 kilograms of useful load. So it's really the flying taxi. So the global weight is 2,200 kilograms. Actually, we have the first version of the propeller, but on the rig we tested already second version of the propeller, which are composite propellers with much better performances. So this aircraft will go also through the incremental and performances improvement using the new technobricks we will put on it. And upper propeller is not shrouded because it's less efficient. And the shroud in forward flight generates the drag. So it was optimized on the rig, and we have chosen the thickness of the shroud to be efficient in hover and not generate too much drag in the forward flight. okay, in the latest one, the racer. So we have, this is the high-speed hybrid formula. This I explain you. So, well, now we have a lot of pieces coming for testing. The latest one, just I saw last week, is the shaft. So in this configuration, you have a supercritical shaft linking the gearbox to the propeller without bearings. Okay, bearingless shaft. So this shaft goes through the critical speed. Okay, the power which goes through the shaft is 1 megawatt. Okay, so this is really very high. So in the middle you have the damper. You must balance this properly, and you have also the flexible coupling, because to compensate the deflection of the wing in flight. So from the both sides, they are done in titanium, and now we will start the fatigue tests, you know, in the laboratory to qualify it for flight. What helps in the integration, X-Cube, it was just simple wing. Here we have this box wing, what is much more efficient because system is stiffer. Okay, stiffer, so the deflection is smaller. So we can also work a lot on the drag. If you want to quickly, as you know, in forward flight, power is proportional to power 3 of the forward speed. Okay, so whenever we can reduce 0.1 meter square meter of the drag, immediately for such aircraft we have roughly globally 2 square meters, you have 5% less fuel consumption. So the drag is key, and for the drag we work on the rotor, of course, all the aerodynamic shapes of the aircraft, a cooling system, to protect the gearbox, intakes, which are dynamics, and this is, I think, very important for this basic aeromechanic optimization is a very important factor even before introduction of new technologies. Whenever we do something, there are several steps in technologies. The first one, doing the good mechanical or mechanical design, optimization, lower mass, the lowest possible the drag, and then all these hybrid improvements, okay, new technologies, and the combination of which can bring breakthrough technologies in terms of the new architecture. I think is, yes, it was. I had 20 minutes time that my communication guy left me. I was 21 minutes, but I'm ready to respond all the questions. Okay, perfect. Perfect. So if any question, you can ask any question you want, okay? The question, if you're here, why we put the duct, okay? Not a racer on this. No. Why we did not use, yes, okay. So I will tell you why we use it on CityAirbus, okay, is really to, the problem of the helicopter is really the hover, okay, is what makes really the power, okay. So this is really where we should improve the power very strongly in the hover. That's why in ducts in CityAirbus in power makes sense, because we put only 20 kilograms of mass, and for each duct you have 100 kilograms more lift. 80 multiplied by 4 is 360 kilograms more of lift without putting any external power for it. 360 kilograms is a bit less than 100 kilowatts, so it's enormous, you know, to keep in hover. And if you have more power, you must put more batteries, you must put more power for engine, and this is a vicious circle in aeronautics, okay? And here, let's say in the racer, hover is given by the main rotor. So no problem, we have the figure of merit of 0.8, very good one. So you cannot put the duct around, okay? And for the propellers in forward flight, we have the efficiency of the propeller is 80% also, and the duct would not help at it. Because in a forward flight, okay, you have so much induced velocity, it's not like in a hover. You have the wind coming and 120 knots in front. In a hover, you have just 15 meters per second. So it's a completely different behavior. The ducted propellers have no sense for the racer. It will decrease the efficiency due to the drag.
But what about safety, for example? In an ultimate,
Well, this is a good question, and it was taken into design compared to the X-Cube. Okay, we have the propellers behind the behind the wings. It's for the safety reason. People can enter in front. Okay. Second things, we will do also the visual detection of the propellers by the RSAS, rotor strike alerting system. So pilot will see exactly how far is from the environment. Okay, and also for application, we can also declutch the propellers in some configuration. So it's should we not help much in this area.
I understand about the aerodynamic performance and the need for an unshrouded or unducted upper rotor on the CityAirbus design. But in terms of environmental noise, that's going to be very important for eVTOL operations. Would you consider that for a production configuration, you might have to compromise a little bit on that and modify the design slightly?
I will do it we don't know up now what will be the production configuration, because we tested several configuration up now, and somebody who thinks that he knows the truth is wrong. Okay, we have a lot of young people and everywhere inventing new formulas, okay, new configuration, and somebody will find one moment. So you don't know what is the final one, okay? But for this one, clearly, when we look at, we went for the simplicity, okay? No, very simple one, nothing tilted, okay? And the best performance in hover with the lowest drag in a forward flight. It was the simple parameter for the noise now. Is clearly very important for it, and it is one of the main challenges for urban air mobility. Nobody wants to hear anything in the city. Okay, so it clearly will be one of the most challenges. So here we have load of the rotor is one of the things, just very unloaded. The lowest rotational speed. And then the electrification is very helpful because it's the problem of failure. When one motor is in failure, another one can go very quickly to the high RPM. And this electric drive is one of the, due to this inherent dynamic, is very efficient. The bandwidth of electric motor is very high. Even we should block it sometimes because you can increase the RPM very quickly. The turbine always the constant, because how the regulation turbine works. You have the sensor on the free turbine. Okay, when pilot increases the pitch, you increase the pitch of the blade, then the power need increases, RPM, rotational speed goes down. Free turbine, which is linked to the mechanical, catches the variation of the speed, okay, and then governing system tries to put the more fuel into the system to increase the power. And this takes a bit of the time, of course, in the loop. Electric system is, of course, very dynamic. Okay, and this can of course bring the value to the system, but also bringing electric system like electric backup system to the turbine is also another opportunity which can be helpful, because you can mix the both, okay, in an optimum way.
First, just would like a confirmation. Is there a physical shaft between the turbine of the racer and the pushers?
And sorry,
physical shaft to transmit the power from the turbine to the pushers.
Yes. It's. Sorry, you want to?
And if yes, did you study the possibility to use an electric engine for the pushers?
Yes, good, clear question, and I think it makes sense. It's what we call it's integrated drive system. So all the systems are mechanically linked. Okay, it's just to the simplicity. The first step. No clutches, everything linked mechanically. It's like in a helicopter, fully mechanically driven. Okay, it was the first assumption we did. So there is, of course, mechanical links. There is supercritical shaft between the gearbox and the propellers, which is mechanically, which transmits 100 megawatt of power. Okay, so it's a good question. Can you make it electric? I will do the comparison. We know it's like small children, small problems, big children, bigger problems. Electrification, okay, will come very quickly to the small sizes, okay, and it is due to the law of physics, okay. There was the genius English aerodynamist called Froude, who verified how the rotor works, is the theory of Froude. And the power, okay, is proportional to the power, let's say, 1.5 of the thrust. So automatically, by the law of mechanics, when you go to the higher application, higher mass, you need more power. Okay, I will give an example. For instance, if you need for 700 kilograms Brunop or 750 kilograms, 100 kilowatt is roughly what we can tell. Okay, if you double it, if you go to 1.5 ton, your power will be at least 300 kilowatts. It's not double, it's much more than that. It's law of physics. On the Super Puma, we install, for instance, 2 turbines of 1.6 megawatts. Okay, so put it electric, it will be very difficult. So your question, if we put electric, you know, here the propellers, you know, we put electric motors of 1 megawatt. Okay, it must be somewhere doubled because you must be justified. So it's already 1 megawatt. Zach, what is the ratio we have now for electric motor? Is factor 5, the weight? So you will have at least 200 kilograms of electric motors, okay? But you must secure them, so it cannot be the simple one because it's much more difficult to justify it, so at least it must be much more than that. It's much more than the price. So then you must generate the current for it. So you must put on the engine, generator. You must have the battery in the system, so everything starts to be very, very heavy and complicated. It's not the case for the simple application like Vahana and CityAirbus, because due to this law of physics, electrification always will come by small sizes. Okay? You can add something if you want to comment something or.
Motors and eVTOLs. We often hear about energy density being a big limitation. When do you think it gets to the point, how many years from now, to where it's feasible to be carrying people?
Well, you can already carry people. Okay, the problem is distance and the mission you want to cover. So it will be the problem of the specification, you know. Of course, if you will have more passenger on board, the mission will be shorter due to the law of physics I explained you. Now what distance want we cover? It will be very specific to the cities. Sometimes the distances of few kilometers, it's enough to transport and to bring the value to the customer. In some areas, you want to go to the airport, which is 50 or 60 kilometers, others is different. So, well, there's no unique solutions. Probably it will be a bit dependent on the area where you introduce this eVTOLs. In some area, perhaps the smaller range could fit.
How far are you with the electric turbine project?
Electric turbine.
Electric backup.
Electric, yes, it's where is it? We tested it already in flight, okay? But it was in 2012, 12 or 13, 12, yes, we tested it. 2011, yes, 11, yes. And I will tell you, we did it, a test in flight, but the battery was a monster, electric was. So now, 8 years later, everything starts to be more attractive, okay? And we should justify it once again, you know, the value of the company, value for the customer. We cannot put just the engineering toys, okay, let's say, for the pleasure. Okay, and with electric backup system, as we discussed last time, you can increase the takeoff weight, okay, of 1 passenger, okay, because we put some mass, roughly 1 passenger mass of the motor and the batteries on the aircraft, but due to the, let's say, always the takeoff weight is fixed by the failure analysis. With extra power on board, we can make this analysis much easier and make aircraft safer. So we can onboard 200 kilograms more of mass. Half of it goes to the system installed, and half is given to the customer. So this once again is the value generation.
In terms of looking at Airbus's overall philosophy approaching the eVTOL generation, Obviously, you've got CityAirbus and Vahana, which are sort of two different approaches slightly. How do you see the evolution going forward? Could you have a Vahana family and a CityAirbus family sort of thing, catering for slightly different parts of the market? Because Uber is looking for at least 3 vehicle types, for example.
Yes, it's a good question. So, well, I don't have 100% response to it because we must analyze it and what we are currently doing. Yeah? So just think what is optimum and what is the way to do it. But, well, I will tell you what it should not be. Okay, it's better for me. It cannot be complicated. Okay, it must be simple and affordable. So always the mixtures of energy. If you put the turbine, it's already complicated. You put electric system on it. Okay, if you then you compute the mass of it, it's complicated. So clearly, for us, it will be not this. So in high architecture, and fortunately, we have 2 formulas. Because it obliges a bit the people to think not only about one solution, and even if we have a bit different teams doing it. So it really generates a value, okay? What is the optimum in this? And I believe that we will converge to something what can make the mission. Perhaps we will start with something what is not 100% ambitious from the beginning, okay? And waiting for the progress of the technologies, but can fulfill some mission of the customers. Of course, it would not be from the beginning something what we respond to all the mission 100%. Okay, but we don't want to make the toys. Okay, it must transport the people. Okay, it must transport people in a significant way. So it's a taxi. Taxi usually you have 4 people on board. Okay, that's the way we think about it. Huh?
How much cross coordination is there between the Vahana and CityAirbus teams? Because obviously you're part of the same family.
100%. Now the team are mixed. Okay, and convergence is done. Phase of working is perfectly aligned, and we are working in a very win-win spirit. Okay, but well, once again, engineering is something what you should challenge the system. Okay, that's where the value is generated.
Just one last question, if I may. What about the subject of morphing blades? I think, under Clean Sky, do you not have some studies underway with...
Changing geometry of the blade. It was the dream, what started, I think, half a century. It will be great, because if we can have the twistable blade, okay, for instance, on the racer in hover, we don't need the twist. We improve the efficiency. In high-speed flight, we need 45 degrees of twist. Okay, so it's clearly the dream. But the problem is, of these elements, they are rotating. Okay, they must be robust. Okay, we must prove even the bird strike, entering into the blade. Okay, so there were a lot of studies with deformation of blades, with mechanical system, piezoelectric system. But up to now, we don't see, clearly speaking, the industrial application. But anyway, nobody knows of this. Up to now, we clearly, in terms of the added value for the flying vehicles, it will be one. Now the industrial application. It's like on a helicopter, in hover, we need some twist in forward flight, no. So it's clearly that it makes sense. Now, how to do it? It's another issue in a cost-efficient way, and it is industrial. You could put the piezoelectric element to deform the blade. Now, piezoelectric elements is quite sensitive. Okay, it's not easy to make it in real life. And blades, they must support the dust, the wind, the water, so it's you must always think about this.
What percentage of Airbus's research and development budget, for example, is steered towards VTOL? Does Airbus consider VTOL to be the next biggest thing in its history, or is it still considering traditional lift as their main focus of business going forward into the future?
Good. I am R&D director in the group, so for me it's not enough. Never I have enough money to make the R&D. If you tell it in this way. But well, how to respond to this to this question, yes, we spent quite significant budget on eVTOL, clearly. Having to demonstrate in flight is not for free. Okay, so this is way company wants to prepare the future. So your clear question is, yes, we are considering very seriously this part of the history of aeronautics. Okay, I will give you another example. You know, we have, for us, the third revolution. You know, the first flight of the airplane was done in 1914 in St. Petersburg. It was only the distance of 14 kilometers, where first time somebody paid the ticket from the flight. 50 years later, we had the tickets for the helicopters. 50 years later, now we consider a third revolution. When we will sell the tickets for this e-taxis, you know, it will come. Huh? So we are ready for it. We are investing for it. Okay. So thank you for your attention. Okay. Thank you a lot.